messaging software and embedded device control systems. Prior to Cornelis, Doug led the software engineering teams at the Red Hat in cloud storage and data services. His career in HPC and cloud computing began at Ames National Lab, a scalable computing lab. He later worked in the Oak Ridge National Lab, where he developed and integrated new technologies at the Oak Ridge Leadership Computing Facility. He holds a bachelor's and master's degrees in computer science from Iowa State University. And he always introduces himself in the MAPITch forum. He actually used MAPITch 1.9. Okay.
I sure did, yes. On old InfiniBand gear that barely held together. It was a real adventure back then.
Yeah, so he's a veteran user of MAPITch over the last 20 plus years. So with this, let's welcome Doug, and he will be presenting an overview of new features of their product.
Thank you. And yeah, I suppose we're at the point now, DK, where many of the people developing MAPITch were not born when I first installed it. So that's might have to go and take a survey about that. So thank you, obviously, for the kind invitation and opportunity to present and sponsor Mug. I'd like to take an opportunity to thank everyone except Hari, who's not here to defend himself, but who sat down with me at dinner last night and asked me if we had any new features that he and the MAPITch team wanted to hear about. So I'm sorry. So Hari kind of spoiled my talk, and I'll give him more grief after that. So this might be a review for just a couple of you that I got to speak to at dinner last night.
Our semester started.
Yeah, he's
today.
probably teaching. Yeah.
Yeah, he went to teach his class.
Yeah. So no, that's it's good because he has already heard all of this. I told him last night. Okay, so let's get started. I think Denny from Cornelis did a good job of introducing who we are. I think most of you are aware of that, so I won't spend a lot of time reviewing us and who we are, but you know that we're a high performance network fabric provider. Our software stack works as much like you would expect. So, kind of starting from the bottom, our switch firmware and software now is all Linux based. And so that provides a lot of opportunity for us to add additional features, both in released software and in the future if our user community is interested in additional features. We use a managed fabric, so we use a fabric manager application to do that, which contains the things that you especially would expect in a subnet manager. So managing the network topologies, routing, presence, security, and so forth. But also it contains a performance manager, and that's something that I'm going to talk a little bit about because although there are only a couple of new features in the performance manager for our next generation products, it's something that I think is sometimes underutilized. And so I want to just give you a little bit of an overview about what features it has and how you can use the performance manager to evaluate the performance or defects in your fabric. And then the fabric executive actually is the means by which user commands are passed to fabric elements, switches, and host fabric interfaces. We have our Linux kernel driver, which you heard a lot about from Denny. We keep that in the Linux source tree, and we have the slings and arrows from Linus Torvalds to prove it. I think now 2 or 3 of my kernel developers have Linus emails on their walls that they wear as points of pride. So the existing driver, as Denny pointed out yesterday, will support both our old and our new HFIs in systems. So there won't be any need for changes or software updates there. We support just both devices in the same driver. And then moving up the stack, our messaging middleware we call OmniPath Express or OPX, and that lives as a provider inside OFI libfabric, with which I know some of you are familiar. And then obviously we have our user tools and so forth. And then we also do some more specific integration with the structured simulation toolkit that I'll talk about a little bit in a future slide. And that's something that we'd be interested in working with the community on to share additional insights. So MAPITch was doing nanoseconds with OmniPath before it was cool. I remember when we first released OPX and broke the microsecond barrier. with OPA 100. I was talking to some of my friends at TAC about that, since we had broken even down below to about 0.8 microseconds latency. And one of the systems administrators at Stampede 3 said, well, with Mvapich, we were at 0.95 before that. So it was neat to see that Mvapich actually broke the microsecond barrier on OmniPath before Intel MPI and other MPIs did. So we use Mvapich, and of course the OSU benchmarks as a first-class citizen in all of our software testing. And then Stampede at TAC will receive early deliveries of our new 400 gig CN5000 HFI. We've made a few enhancements to our driver. One is direct support, hardware support for virtual machines, SRIOV. So there are the API changes that are needed from the kernel level are all very minor. And we've already implemented those in our middleware in OPX, which is open source. So you'll be able to see those or consult with us if there are any changes that you need to make. From an Mvapich perspective, at that level, no changes will be needed, since it all just runs through libfabric. Denny mentioned that we're sticking with uverbs for now. And we might use that to swallow our the file descriptor we used before. We're also investigating IOU ring heavily, since it seems to provide a way to drastically lower system call overhead. But so far we've seen slow uptake from Linux distros on it. So we'll support it when we're confident that it has wide support. And it should be relatively simple for us to integrate at that point. We're interested. If you've had any experiences using it for anything, we're interested to hear about it. But otherwise, we'll move to adopt when we see it filter down to actual installed Linux distros. So all the stuff that I just mentioned above, our libfabric provider has the changes for it. And not everything has made it to the upstream kernel yet, but we've got some of the RFCs in flight to get the material all upstream. So I think most here are familiar with libfabric, so I won't spend a ton of time on this overview. But the key really takeaway from learning about libfabric is that it provides this abstraction layer, which allows us to advertise our fabric features to higher level middleware like Mvapich. And then it allows higher level middleware to then match the needed features to the functionality provided to its users. So a good example of this is Mvapich is able to handle a lot of GPU data transfers on its own and doesn't require GPU support from us in the OmniPath Express provider. So although we advertise that support, Mvapich, for example, chooses not to use it. Other MPIs do. And so this allows us to make sure that the applications receive the best possible performance based on what Mvapich knows and needs, or based on what we can provide, knowing less about the semantics above us. It's great because it's really just, you can think about it as a really thin matching layer in between the higher level middleware and the fabric interface. It's worth mentioning here, my last bullet, that just like the old device driver will support our new hardware, so also will OPX support our new devices. And in fact, OPX is really developed with those new devices in mind. We did originally write it using our existing OmniPath as a prototype, and you're welcome to try it today. It runs great with Mvapich. And that'll be the primary use case for quite a few of our deployments, as I understand it. We support a broad range of those OFI services that are needed by upper level middleware. But if there's an implementation you're doing, whether it's something inside something like Mvapich or even a direct application that needs support for additional primitives, let us know and we can implement them. One of the primitives we implement is the hierarchical memory transfers. So that's how we support GPUs in our software layer. But again, you can do it yourself if you like, and Mvapich certainly does that. libfabric 2 is coming, and OPX will be available on as part of libfabric 2 as well. Not only will OPX drive both of our cards, but it will drive them together. So if you have a mixed fabric, you can simply you can use OPX for all that communication. All right, so some things that we've added. So first, we've added a low-level tracer that's a little bit like MPIP if you've played with that before to OPX. So if you're interested in getting maximum performance on OmniPath networks, you can do profiling down at the libfabric layer. You can also, if there are more interesting performance trace points, as everything is open source, you're welcome to collaborate in that or contact us, and we're happy to extend the number of trace points. We've had a great time with this internally because we've been able to use it to optimize performance for new platforms. Right, every time somebody releases a new CPU, it has different performance characteristics, and we can see that. Right, when our latency is under a microsecond, even extra branches we have to take, any mappings between cores and sockets, or cores, sockets, NUMA nodes, everything results in different performance characteristics. And being able to do low-level performance modeling like this really helps us fine-tune for new architectures. And this is especially important as there's more innovation in CPU and GPU design. So it's also something that I think would be helpful for middleware implementers that are implementing middleware on top of OPX and exploring performance differences for new platforms. So it's something that might be interesting to an MBAPIC audience. And just real quick, here's an example. These two traces are not to scale, but here we were able to improve this particular transfer from 17 to 5.5 microseconds by using low-level profiling. So happy to dive into the details if anybody's interested, but I thought this was neat and figured I'd share it with you all. Something that I don't think we talk about enough in groups like this is network health and monitoring. Obviously, in most cases here, we're concerned about scalability and performance. But I learned from my days at Oak Ridge National Laboratory that when you scale systems, you also scale failures. So monitoring and understanding the behavior of systems is critical to the operation of any system at scale. So with since we rolled out Linux on our switches, now we can run reference implementations from DTMF. They implement the Redfish standard, which is a REST API for device control. So it's kind of like something that I see as replacing IPMI in a sense, but it has a little bit more functionality. So you can do, of course, your basic queries. How fast is my fan spinning? What's the temperature of my ASIC? So forth. But you can also issue complicated queries and device commands via Redfish. And already all the standard tools work simply because we started from the reference implementation. But of course, we've added and contributed upstream the OmniPath specific bits. Also our switches through their congestion avoidance and adaptive routing algorithms produce additional telemetry about the congestion state they're experiencing, because they gossip among themselves about their current congestion state. And we can extract that and display it for users to get an idea of exactly what's going on in your fabric. This will make a lot more data available programmatically. We still have the CLI for everything that you're probably used to using if you've ever administered an OmniPath fabric, but we're making a lot of this available via APIs so that you can integrate with your own tools. So in fact, users of Prometheus, Grafana, and other types of monitoring and logging tools and so forth can already, with no changes, plug into the Redfish API that we use here. And then as an extension to make the fish analogy even more confusing, the Open Fabrics Alliance introduced a standard called Sunfish, which has additional primitives specifically designed for managing high-performance fabrics. And so we're involved in the development of that standard, and we'll continue to join with that, and we'll support Sunfish as soon as it's released. So we're also collaborating with the community to support the lightweight distributed metrics service, which is developed mostly out of the National Nuclear Security Administration labs, but I see it used to handle data collection for components on a number of different supercomputers. So if you've never looked into it before, it's actually it's fascinating. It has the ability to define and create metric sets for all sorts of different types of values in a complex system. So for us, that includes things like performance and other hardware counters, but also for various components like power states and memory errors. Also kernel counters, for example, if you want to pull things like cache misses or things like that out of individual nodes. It's capable of collecting, disseminating, and storing large amounts of this data in a scalable way. So it's really impressive, and we'll integrate directly with it with our new Switch platform. All right, so as I mentioned, I wanted to dive in just a little bit into our performance manager, just because I see a lot of people haven't heard of it. And I think it's really useful in getting information about and diagnosing application issues as well as network issues. So our performance manager lives inside our fabric manager. So it comes part and parcel with the FM when you start it up. And by default, it piggybacks on the FM's fabric sweeps in order to gather performance information from every switch and host fabric interface in the system. It stores that information in a database that you can query. And of course, all this is configurable. You can configure things like the sweep interval as with any fabric manager. You can configure also the how much data is stored and for how long and so forth. But you can also query this data directly from the fabric manager, so it isn't necessary to sweep the fabric every time you want to get a piece of information like how many nodes are showing link errors or are experiencing congestion or so forth. So here's just a few examples of queries you can make. So most of them are pretty obvious to someone steeped in our field. But I'll mention a couple. One, obviously, if you want to grab the topology, you end up with a topology file that you can then use to instantiate the same routing algorithm or topology on your network in the future. Why is this useful? Because then if you save this topology output, you can ensure that your network isn't tampered with by any additional devices. So you can essentially freeze the topology at what the fabric manager currently detects and cause any other node that attempts to join to cause an error. And so, of course, you can also do your basic node queries and things like that you're very accustomed to on high performance fabrics. Get routing information and so forth. But it's the last one that I find the most interesting and is often the most unexpected. And that's we essentially have a top application. And so when you run this, it gathers the performance information from every sweep and displays it live. So you can observe congestion points. You can observe pathologies in applications, which may cause you to want to distribute your applications differently across the system, maybe run more or fewer processes per node. We've seen with things like climate models that run multi-physics, where different parts of the physics may benefit from different topologies, different numbers of processes per node, and so forth. And so OpenTop is a great way to be able to diagnose that. As you run it, you can move forward and backward in time back up into the earliest parts of the database that you had the performance manager save for you. So by default, you can rewind hours into the past. You can save snapshots of interest and compare them. It's a great both application analysis and fabric analysis tool. And if there are other tools that middleware developers would be interested in, I'd love to hear about that. Because our new API makes it pretty easy to add these kinds of things. And so I want to make sure that we're providing our users with everything they need. We're also doing a lot of work with the structural simulation toolkit that comes out of Sandia National Laboratories. SST, you can think about it. I was trying to think of a concise way to explain it here. What I came up with was it's a little bit like a multi-physics code for network simulation. So if you look on the right, you see that all of the various parts of the simulation software are componentized. So there are models for example, your CPU, even your memory, PCI bus, network switch, and network card, all of which are dynamic and replaceable. So they've done a bunch of different studies over the years of different characteristics of network hardware and used it for modeling of things like benchmarks and job suites and so forth. And so what we use this for is we use it to tune our routing algorithms, our hardware, and we use it to predict performance on applications on different platforms. This is all an open source project, by the way. And so it's very easy to grab the head of the branch and look in advance at what the implications of your topology and hardware are like for various applications. So we're contributing our own hardware model to perform some of these studies, and we're also helping to enhance the remainder of the models. For example, the network software simulation layer we're helping to replace with libfabric. So doing a lot of work as part of this collaboration, and it produces very interesting results. So if there's interest in doing things like topology studies for specific applications or collective algorithm studies for different topology networks, this would be something that we could have a conversation about, and I'd enjoy that. Okay, and then some new hardware features that may be useful to messaging libraries. I'll say at the start, as I was talking with some of you last night, these features are ones that we implement in our own libfabric provider, but they're ones that we could, if it were of interest to you, expose to higher level software. So for example, our dynamic routing is user controlled. It's in fact available on a per packet basis. So we at our level can figure out based on what we know of the semantics, what it's possible to dynamically route. But if you're writing a higher level messaging library or abstraction or application, you might have a better idea. And so maybe we could expose that to a higher level messaging library and see if we could get better performance on especially advanced topologies like Dragonfly and Megafly. We also have hardware receive side matching rules. So these are essentially some deep packet inspection that our host fabric interface can do on receive in order to direct packets to the proper receiving process. So we use this internally for a number of different functionalities, but we greatly expanded the number of rules and their sophistication in the CN5000 timeframe. And so if there's a way, for example, to use this to do some message matching, then maybe that is something that we could expose to a higher level of software and see if that's something that you would all want to use. So we also have a receive cut through feature, which essentially lands packets as they are, lands data as it arrives rather than packets as they arrive. So it'll land the beginning of a packet before the end. Now there's a big danger flag for that, right? Because the data lands before we've had a chance to do the CRC on everything. But if you're doing things, I've heard some conversations, for example, about that Mvapich is thinking about doing in-flight data compression, right? And so whatever decompression step you're doing is implicitly a data validation step as well. So if you're doing that, there's no danger that you're going to return bad data to the user if your decompression step fails. We can trigger a recovery at that point, for example. So maybe this is a place where we could save some latency if we exposed it to higher level software. And then finally, we have a receive bypass feature, which essentially allows us to open wider RDMA receive memory windows on the receive side. And again, this obviously works as a great message optimization for us. But I can also see some ways that higher level software might be able to use it. For example, if you have a systolic application that has a consistent message pattern, then we could pre-configure some of these windows in advance in order to, for example, possibly save a round trip for a rendezvous.